Okay, so the gravitational force and weight. In general, the gravitational force is the force that the Earth exerts on the object. Now, you need to pay attention that the gravitational force is a vector and all the time is directed toward the center of the Earth, downward. Now, the weight is the magnitude of the gravitational force, as you can see here. So, weight is the magnitude of the gravitational force, which is m times g. So, m is the mass of your object, g is the gravity constant. Now, let us look to this example. We have a box rests on horizontal surface or table. So is the weight vector all the time downward with magnitude of m times g. Newton's third law. So here we are talking about pair of two forces, action and reaction. So you have to know in this law, the action and reaction have the same magnitude, but opposite direction. And the best example I'm going to speak here is from your textbook, swimming pool. So suppose you are at rest in a swimming pool, as you see here. First of all, if you push the wall with your legs, the wall will exert a force that propels you further into the pool. So we have the action force, as you can see here. This is the first force. Now, the reaction is coming as the following. The wall exerts on you as opposite in direction to the force that you already exert on the wall. So we have now pair of two forces, F from the wall and force from your leg, or I call it F person. So as I mentioned before, those two forces as action and reaction have the same magnitude but opposite direction. So in magnitude, they are equally magnitude, but as a in vector notation, the first force equals minus the second force, or the action and reaction. Now the normal force, please pay attention to this slide. When we are talking about normal force, we are trying to look to the force exerted from the surface to your object. So whenever the object is in contact with the surface exerts a contact force on it. And please be careful, this normal force all the time should be perpendicular to the surface. So the angle between this vector and the surface is 90 degrees. So what will happen if we flipped this system upside down? This is the surface and this is the object, and we are looking to the component of the contact force that's coming from the surface. As you can see here, the angle is 90. Okay, what about if we take the surface along y-axis and put the box or the object, as you can see here, the horizontal, or I'm sorry, the surface will exert a contact force perpendicularly to the object. Here, for the inclined surface, and I'm going to have 2 or 3 examples later about this type of surfaces. So we have an inclined surface with angle of inclination theta. This is my object, rests on it. And please, here, this surface is the x-axis. So the normal force is a perpendicular on it and has a 90 degrees, as you can see. Okay, now let's go the funny part, which is examples. So I'll start with example 5. An object whose mass is 2 kilograms moves on a table as shown below. First, find the magnitude of the normal force and find the magnitude of the acceleration. So my advice for all of you before you start or you go to the solution, try to draw all the forces acting on your system. So as you can see here, I have a normal force perpendicular to the surface, weight perpendicular to the surface and downward, force, this is my force along x-axis. Here, my object or the box or the mass rests on a horizontal surface, means the motion is to the right because I have a force here. So to calculate the normal force, we are talking about y-axis. And since there is no motion along y-axis, summation of Fy equals 0. So I have normal force positive, weight is negative, so N minus W will be 0, and then the normal force will be 2 times 10, which is 20 Newton. Now to calculate the magnitude of the acceleration, I'm going to read the x-axis, which is summation f of x equals m times a. I have only one force and it's in the same direction of the motion, so it's going to be positive f equals m times a. Substitute the force and the magnitude of the mass, it will end up with a equal 50 meter per second square. The second example, a box of mass 7 kilogram pulled to the right. Okay, here the direction of the motion is given, which is to the right, as shown below on a smooth horizontal surface. Find the box's acceleration and the normal force. As I mentioned before, please draw your system with the whole forces acting on your object. Okay, so x-axis and y-axis, the normal force is a upward vector, the weight downward, as you can see here, and both of them perpendicular to the surface or perpendicular to the x-axis. But the difference between this example and the previous one has a horizontal surface, but here my force has an angle. So I have to get the two components of this force, which is F along x-axis, which is F cosine theta, and F along y-axis, which is F sine theta. Okay, now to calculate the acceleration, my object is moving along x-axis, not y-axis. Again, my object is moving along x-axis, not y-axis. So the acceleration will be along x-axis. So summation f of x equals m times a. Here I'm taking the x component of the force, which is 100, times cosine 37, which is 80 Newton, equals 7 times a. To your calculation, you will get a equal 11.4 meter per second square. Now to calculate the normal force, as you can see here, the normal force in y-axis, and there is no motion along y-axis. So summation f of y equals 0, normal force plus Fy minus W equals 0. Do your calculation, you will end up with normal force equal 10 Newton. Another example, I have two masses, 2 kilograms and 4 kilograms, are connected by a light string. A force of 100 60 Newton is exerted on M2. Determine the acceleration and the tension. Okay, so to do this one, okay, so before we go to calculate the acceleration and the tension and the strength, you need to pay attention to the following. This string is a massless, which means that the net force on the string must be 0. This number one. Number two, let me delay it and try to draw the forces acting on this system. So as you can see here, I have M1, so normal force, and W1, and I have M2, so M2 and W2. The force is acting, the acting force here, as you can see. So now for this string, as I mentioned before, it's a massless. Therefore, the net forces equal 0. This leads us to conclude that the force it exerts on the two boxes or masses from the string are equally in magnitude, but oppositely in direction. So that's why we have T and T. I gave them the same magnitude. Okay, now to calculate the acceleration of the system, I have two, or actually I divided this system into two systems. Okay, summation f of x for the first mass equals m1 times a. As you can see here, one second, please. Okay, so now, as I mentioned, summation f of x so equals m1 times a. So this is my system for the first mass. I have only f, same direction to the motion, minus t. Here t taken minus sign because it's the opposite direction to the motion, equals m1a. For the second mass, I have only one force, which is the tension. So summation f of x, which is t, equals m2 times a. Now I have two equations with two unknowns. So the best way is for me just to take the first equation, add it to the second equation, because I have here minus t and plus t, they will cancel out. We'll end up with f equal m1 plus m2, all of them times a. So the force is 160, m1 plus m2, which is 2 plus 4. Do your calculation, you will get acceleration equal 26 meters per second. The second part, to calculate the tension. Okay, so we have here two equations from two masses, or from my system, which are f minus t equals m1a and t equals m2 times a. So we already calculated the acceleration. So all what you have is just substitute your acceleration either in the first equation or the second equation. You will get the tension equals 104 Newton.